So hello, everybody. Welcome to the Atto Fridays. Our speaker today is Professor Mike Chini. He's an associate professor of physics at The Ohio State University, and his research focuses on the experimental strong field physics and attosecond dynamics, and it involves many aspects of laser science, ranging from the development of lasers and secondary sources, nonlinear optics, ultrafast metrology, and intense laser meta-interaction. So a lot of stuff. He received his BSc in physics from McGill University in 2007, before beginning graduate school at Kansas State University, where he worked in the J.R. McDonald Laboratory, and then he moved to UCF, University of Central Florida, where he completed a PhD in physics in 2012. He remained there as a postdoc in the group of Chengju Shang and as a research scientist in the group of Mark Richardson and as a faculty member in physics from 2015 to 2024 before moving to OSU in 2024. He's a recipient of an Air Force Office of Scientific Research Young Investigator Program Award, the Department of Energy Early Career Research Award, the Oak Ridge Associated University's Ralph E. Powell Jr. Faculty Enhancement Award, and is a fellow of Optica. So welcome to the Atto Fridays, and it's great to see everybody here after the spring break. And the floor is yours, Mike. Feel free to take it, and we hope you all enjoy the talk.
All right, thank you very much, and thank you for the kind invitation to speak. So today my talk is focusing on attosecond electronics, laser waveform control of electron dynamics in materials. And before I start on the technical aspects of the talk, I just want to give a quick plug for my group. So as Carla mentioned, I've recently moved to Ohio State University, and so I have a new group at Ohio State called LEAP, Light Wave Electronics and Attosecond Photonics, where we focus both on the development of new attosecond light sources and also the application of attosecond science to study laser influence on material properties. Okay, so this whole field of research is really motivated by enhancing the speed limit of electronic processes. And so here's a plot that I'm sure many of you are familiar with from a review paper by Ferenc Krauss and Misha Ivanov in 2009. And essentially it links the timescales of processes in matter to energy levels in different systems. And so, for example, if you look at the picosecond timescale and nanometer spatial scale, we can see that the energy level spacings associated with vibration are on the order of tens or hundreds of millieV, and so this sets the time scale to be on the hundreds of femtosecond to picosecond time scale. As we move to electronic states, things become faster. So in semiconductors, band gaps are around 1 eV. In dielectrics, it can go up to 10 eV. In atoms and molecules, we have valence electrons, which have energy level spacings on the order of several eV, and core energy level spacings on the order of several tens or hundreds or keV. And so this brings our timescales down to sub-femtosecond in semiconductors and dielectrics, down to the few attosecond timescale in atoms and molecules. It turns out that we can also think not just in terms of free energy levels and wave packet dynamics in matter, but rather we can also influence attosecond dynamics and drive attosecond electron processes through laser-driven dynamics. And so this was really, I think, at least in solids, first introduced by Schulze et al. in 2013, where they showed that if you look at the transient reflectivity signal from a silicon dioxide sample close to the damage threshold, then essentially what they saw was that you could modulate the reflectivity of this sample with sub-cycle precision. And so these oscillations in the reflected signal are really happening are reflecting dynamical changes of the material properties that are happening on sub-cycle timescales. This was later advanced to actually give the prospect of creating devices. So here, again, using silicon dioxide and putting putting gold electrodes on it to detect a current, essentially what they showed was that you could use this same type of technique to measure things like the laser electric field waveform or the carrier envelope phase of a pulse. And so this is really a transition from looking at laser-driven attosecond dynamics to now kind of proof of principle demonstrations of device scale physics. Okay, and this actually has potential for technological applications. So in scenario one here, I have a cartoon from Mohammed Hassan's group at University of Arizona, where they're looking at using multi-octave light sources in order to create attosecond field transients, okay? And so from there, by using an accurate temporal characterization apparatus that can resolve now the electric field oscillations of the light, then what they proposed is that you can use this as a way to create logic devices capable of encoding memory with sub-femtosecond precision. In a second, perhaps more, let's say, futuristic application, Mac Kira at the University of Michigan has proposed the use of this same type of technique to drive light wave quantum processing. And so this is a figure from Mac. And so essentially the idea here is that one of the big bottlenecks in terms of quantum information processing has to do with the ability to perform operations within the coherence lifetime of the system. Now, typically, this is overcome by using systems that have extremely long coherence time, either by going to very low temperature or finding good qubits with very long coherence times. But if we just think about the kind of standard semiconductor technology that all of our electronics currently rely on, is based on silicon at close to room temperature. And so there we have a coherence lifetime on the order of 100 femtoseconds. And so what has been proposed is that you can consider a case where perhaps you can encode some kind of quantum information into the Hilbert space of a traditional semiconductor. And then if you have the ability to both clock with few femtosecond precision the processes that you're able to create, and also to drive logic operations that basically interact with this entangled information, then it's possible, perhaps through optical process, like optical readout techniques, to read out that quantum information. Okay, so in order to advance these ideas, then we need to think about what are the techniques that we need in terms of our toolbox for attosecond electronics. Okay, and for that, we kind of need three different tools. Okay, so first of all, we need what I'll call our function generator. Okay, so we need something that can actually that can create optical fields with controllable properties on sub-cycle timescales. And so this is going to be, our function generator is going to be optical field synthesis and control. We also need a way that we can actually read out what are the sub-cycle dynamics of the fields that we create and then manipulate. And so it's in electronics, that would be something like an oscilloscope. Okay, and so for optical fields, oscilloscope is too slow, but we have the capability now to use optical field sampling to read out information with sub-cycle precision. Okay, and then finally, we need something that we can use to extract high-order frequency responses, perhaps that are beyond the reach of optical field sampling. So something like a spectral analyzer in a conventional electronics picture. And in our case, for attosecond electronics, this will be high-order harmonic spectroscopy. And so I'll spend a little bit of time talking about each of these. Okay, so the first is that we need to be able to synthesize optical fields with a high degree of control. Okay, and so the good news is that this section can be quite short because we're very good at controlling optical fields already. And I think that this is really highlighted by a series of Nobel Prize winning advances. Okay, and so the first, even before the invention of the laser, people were thinking about how we could use well-controlled light in order to study ultrafast processes. And so the Nobel Prize in Chemistry in 1967 was given for flash photolysis. And so this was using incoherent light, but short bursts of incoherent light from something like a xenon flash tube as pictured here. Of course, soon after the invention of flash photolysis, we had the creation of the laser. Okay, so here's a picture of an early Ruby laser. And of course, this won the Nobel Prize in 1964. So now we have the ability to create and manipulate coherent light. Now, with coherent light, this was, initially CW or long pulse light. But in 2018, we have the Nobel Prize for chirp pulse amplification, which now allows us to take the coherent light from lasers and really manipulate it in new ways, to take the pulses from a laser and make them very short and also make them very intense. And to control the spectral phase in such a way that we can shape the pulses and shape the time-dependent frequencies that occur within a pulse. We're also very good at manipulating the spectral range in which the light is generated. Okay, and so for this, we have the Nobel Prize in 1981 for laser spectroscopy and nonlinear optics, and also the Nobel Prize in 2023 for attosecond pulse generation. And then finally, we now also have the ability to control fields even down to the most precise level on the sub-cycle timescale through control over the carrier envelope phase. And this, I think, is really highlighted by the Nobel Prize in 2005 for frequency combs. Okay, and so from all of these incredible advances, we now have the ability to control essentially every property of light, I would say, to the same degree that we were able to control microwave fields at the dawn of the transistor era. Okay, so today we have the capability for arbitrary optical field synthesis. So for example, if we want to say we have some pulse and we want to push down the satellite or the wings of the pulse, well, we can do that. Or if we want to make it a bit more intense, then we can pull the field and make our fields more intense. Or we can chirp the pulses and change the spectral phase of our light. Now, this is not so easy to do in the lab, but it's possible. So essentially, the requirements that we need to have are very broad bandwidth, ideally expanding to an octave and beyond if we want to be able to directly detect things like carrier envelope phase. We need relative phase control so that we can actually make our pulses very short, or that we can shape them in the way that we would like to. And then we need to have carrier envelope phase control so that we can manipulate these subcycle fields. If we want to do this in materials and conventional semiconductors, then we would like to reach the strong field physics regime. And so that means working with frequencies of light that are below the band gap of the material. And so all of these requirements need to be extended now to the mid-infrared in order to work in semiconductor technology. So how do we generate these short femtosecond mid-infrared fields and then manipulate them? Well, the first step is that we generate them through optical parametric amplification. So optical parametric amplification is a process through which a signal pulse, which has lower frequency than a pump pulse, is amplified, and in the process generates an idler through a nonlinear second order process difference frequency generation. And in our lab, we do this with a two-stage parametric amplifier that's pumped by an ytterbium-doped potassium gadolinium tungstate laser amplifier in two stages. So in the first stage, we have a BBO parametric amplifier that's pumped with 515 nanometer light to amplify a 795 nanometer signal and generate a 1460 nanometer idler. That idler is then sent to a second stage of parametric amplification. It's used as the signal in a KTA amplifier, in this case pumped with 1 micron and generating a 3.5 micron idler pulse in the mid-infrared with 90 femtosecond pulse duration. Now, through this parametric amplification process, we get relatively long pulses. 90 femtoseconds is about 10 optical cycles at this wavelength. And so we need to then also compress these pulses to few cycle durations. And we do that through a nonlinear self-compression process that takes place in bulk solids. So we use a set of plates, in this case, a YAG plate sandwiched between two silicon plates. And from the nonlinearity, we broaden out the spectral bandwidth. So this is a technique that was first proposed by Jiro Itatani's group in 2018 to use the combination of these three materials. And so we can generate really quite broad spectra covering around an octave of bandwidth. And so this is a measurement of the close to 2 cycle pulses that we measure in our lab based on this nonlinear self-compression technique. It turns out that we get carrier envelope phase control for free in this process, and that's because parametric amplification provides passively stable carrier envelope phase. So just like we have in the difference frequency generation process, the idler frequency is equal to the difference between the pump and the signal. It turns out that the phase of the idler is also proportional to the difference between the phase of the pump and the signal. And so if we're able to set up our parametric amplifier in such a way that the pump and the signal pulses in our final stage have the same carrier envelope phase, then these two contributions cancel out, and we get a carrier envelope phase for our idler that is equal to a constant. Of course, we need to characterize this experimentally. And so we do this using a technique known as 2F to F interferometry. Many of you are probably familiar with F to 2F interferometry, and 2F to F is the same, except that we reverse the order of the supercontinuum generating crystal and the second harmonic generating crystal. Okay, and so we can make measurements that give us information about the carrier envelope phase stability. So from this interferometer, we measure fringes or interference patterns that are in the spectral domain. And based on the stability of these fringe patterns, then we can say something about the stability of the carrier envelope phase. So I just want to highlight here that we have a steady interference pattern that indicates stable carrier envelope phase. And then if we insert a pair of calcium fluoride wedges in the beam before our 2F to F interferometer, we can actually scan the positions of the maxima of those interference patterns, as you can see in this lower right-hand panel, which indicates that we can control the carrier envelope phase. Okay, so that's really it for the generation of these few cycle mid-infrared fields. And so the next thing I want to talk about is optical field sampling. And the technique that we use in my group to do optical field sampling and some of the things that we can learn from optical field sampling measurements. Okay, so the measurement of the electric field of an optical pulse is something that's quite challenging traditionally to do. This is because the time scale of the oscillation is on the order of about a femtosecond or a few femtoseconds. And so in order to characterize the electric field, we would need to have some kind of way to sample that with precision well below the time scale of the oscillation period. This was first done through attosecond streaking. And so the way that attosecond streaking works is illustrated here on the left panel from Marcus Drescher's paper in 2002, where they showed that by using an attosecond pulse and a time-of-flight spectrometer, they were able to sample the momentum kick that electrons ionized by the attosecond pulse would receive in the electric field of the pulse of the near-infrared field that would either accelerate the electrons towards the detector or decelerate them so that they were going towards the detector with lower speeds. Okay, and so basically, by looking at the momentum of the electrons when they reach the detector, one can sample the vector potential of the laser field. Okay, and this was was shown in this really beautiful work by Eleftherios Gouliamakis in 2004, where he showed here the attosecond streaking spectrogram showing this momentum shift. So this is showing kinetic energy, but essentially, you have electrons that are coming with less momentum or more momentum, depending on the time when they arrive, the time that they're ionized in the laser field. And from that trace, they were able to trace out, from that streaking spectrogram, they were able to trace out the electric field oscillations of the light, and then compare those electric field oscillations to a measurement just based on the spectrum of the light and assuming a flat spectral phase. And so here they're showing that they have a pulse duration that's below 2 optical cycles in this measurement. Now, it turns out that we don't necessarily need to have an optical field that can probe these sub-cycle variations. So in the case of attosecond streaking, you have an attosecond pulse, which has duration that's less than the cycle, the optical period of the laser field. And so generating an isolated attosecond pulse is a challenging experiment. And so there's been a good amount of work looking into ways that we can create this sub-cycle probe without all of the infrastructure and ultra-high vacuum equipment that's required for attosecond streaking spectroscopy. And so it turns out that tunneling ionization can also provide this sub-cycle probe. And so this was proposed by Kyung-Taek Kim's group in 2018. And so essentially the way tunneling works, right, is that you have your Coulomb potential that is distorted by the electric field of the light. And so this creates a barrier through which a portion of the ground state population can tunnel out. And of course, this is linked to the, very closely linked to the electric field amplitude at the time of the ionization event. And so the tunneling rate actually is very narrow in time, and is highly localized during the region where the electric field amplitude is maximal. So this sub-cycle probe can then be used as a way to measure the electric field amplitude of, or the electric field of a light pulse. And so to illustrate that here, I highlight, so this is assuming a 3.5 micron field. And so I have a strong field in red, which is initiating the tunneling. And I have a weak field, which perturbs the tunneling process in blue. And here I've amplified the scale of the blue pulse just so that you can actually see it on the same scale. But this is quite weak, about 0.1% of the field that initiates the tunneling. And what we can see is that depending on the time delay between those two fields, the tunneling rate can actually be modified significantly. So here in red, I show the tunneling rate from the red field alone, so the strong field alone. And then in blue, I show the modified tunneling rate due to the addition of the weak field. And so what you can see here is that when the weak field is added up in phase with the strong field, then this leads to a strong enhancement of the tunneling signal. So we get a large difference in the tunneling rate, despite the fact that this field is quite weak. If we then change the time delay so that those fields are adding up out of phase, then what we can see is that the tunneling rate is suppressed, right? And so this is telling us that the tunneling probability can give us some information about the time delay and or about the electric field of this weak pulse that, in this case, we would like to sample. Okay, so this was demonstrated by Kyung-Taek Kim's group in Korea, first in gases. And so essentially they built an interferometric setup where they focused their both strong and weak fields in between two metal plates and detected the current between those two. So seeing how many electrons had been ionized. And what they showed in those measurements was that they were able to trace out the electric fields of their light pulse, and also that this measurement is sensitive even to the carrier envelope phase. So this is plots for two different carrier envelope phase measurements. In my group, we worked to push this technique to solids. For one reason is because it's with low pulse energy mid-infrared light, it's difficult to ionize noble gases. And so instead of using noble gases, we used a crystalline target. And instead of detecting directly detecting a current, we detected a fluorescence emission from that was excited from the nonlinear interaction of the mid-infrared field with, in this case, a zinc oxide crystal. Right, so zinc oxide has a band fluorescence emission that occurs at about 390 nanometers. And so by monitoring the amplitude of that band fluorescence emission, we were able to trace out the electric field oscillations of, in this case, a mid-infrared field with a roughly 3.5 micron wavelength. Now, these measurements are very nice, right? So now we have a way that we can measure electric fields of light without having to generate an isolated attosecond pulse. However, the measurements are still challenging to do. They require a stabilized interferometer. So in this case, we actively stabilized our interferometer using a continuous wave green laser that co-propagated with our experiment. And of course, in order to do this measurement where we're scanning the time delay, we're inherently averaging over many, many laser pulses. So it would be really nice if we could adapt this kind of technique to a single shot measurement. So how does single shot measurements tend to work? So we can think about doing field sampling in a single shot measurement. And in this case, the solid sample really helps us a lot, okay? And that's because our solid sample can serve as essentially like a two-dimensional plane over which we can make these measurements. And so, for example, if we take our strong field, or strong pulse from the intense arm of the interferometer, and we shine this onto our solid sample, and let's say we measure a signal that could be a fluorescence emission, then essentially what we're measuring is somehow the excitation probability as a function of position. And if we look at what that will look like, we'll see that it's, kind of follows something that that depends on the beam shape, the shape of this laser field. Of course, the excitation in this case is nonlinear, and so the distribution that we'll measure will be narrower than just the beam shape itself. We can then add a weak perturbing field that comes in at a small angle with respect to the intense field. And in that case, what we'll measure is something that has an additional interference oscillation on top of it. So for a lot of the trace, it will look essentially identical to our strong field alone. But near the center, if the time delay between these two pulses is set to 0, then we'll measure an additional interference pattern that gives oscillations on top of this signal. Now, why does this happen? We can understand from other nonlinear techniques for single shot pulse measurements. And so essentially this happens because what we have are two pulses that are coming in at a small angle. In space, each of those pulses looks something like a pancake, okay? And so if I cross the two pancakes, then they overlap in time at one position near the center of the sample. In this case, the top, pulse number 1 arrives earlier in time than pulse number 2. And if I look on the bottom, then pulse number 2 is arriving earlier than pulse number 1. And so essentially, when we cross these two beams on our detector, on this two-dimensional detector, then what we have is something that we can map now lateral position to a time delay. Okay, so we realized this experimentally. So we took our fuse cycle mid-IR beam, we split it into an intense, what we call fundamental pulse, which has most of the energy, and a weak perturbation pulse, which has about 0.1% of the intensity of the fundamental. And we combine those on a concave cylindrical mirror and put them spatially and temporally overlap them onto, in this case, a silicon-based CMOS camera. So here, what we're doing is rather than now detecting a fluorescence signal, we're detecting directly the nonlinear excitation of electrons within the CMOS camera. And so we have a essentially a pixelated detector that is serving both as the nonlinear medium and as the excitation detector. And from that, we're able now to use this crossbeam geometry to map the time domain oscillations onto the spatial dimension of the camera. Hey, we also want to measure carrier envelope phase. I'm not going to go into the details of exactly how that works, but the way that we measure that we characterize the absolute carrier envelope phase of these pulses is that we add also a second harmonic field to our perturbation arm, and we simultaneously measure the second harmonic field and the modulations from the perturbation field. Okay, so this is what the image looks like on the camera. So if we have only the fundamental, then we see that we have some kind of a spatially varying excitation signal. When we add, in this case, a multi-cycle perturbing pulse, then what we can see is that the pattern on the wings doesn't change much, but in the overlap region, we can see that we have this additional modulation that's happening on top of our excitation signal. We can take a line out of those two signals, and we can see that we can extract this oscillation. In order to extract the waveform, we need to somehow eliminate the contribution from this, let's say, slowly varying background signal. And it turns out that this can be done quite easily using an analytical normalization procedure. And in this paper, we show that this normalization procedure is valid both in the tunneling and multiphoton ionization or excitation regimes. And so it's quite general. So then we combine our fuse cycle mid-IR and the second harmonic perturbation. And so we can then get our electric field waveform and truly measure this now in a single shot of the laser. And so each of these gray curves is representing one laser shot. And this red curve is representing the average of 10 measurements. Now, looking at this, you might say, oh, look at the signal to noise ratio on the wings of your single shot measurement is really quite bad. But it turns out that the noise doesn't overlap at all largely doesn't overlap in frequency with the pulse that we wish to measure. And so that's highlighted here in this plot on the bottom, where I show a measured spectrum with a Fourier transform infrared spectrometer, and then the spectra that we retrieve, the spectrum and the phases that we retrieve from each of the single shot measurements, along with the averaged measurements. And so what you can see here is that even though there is a significant deviation in the wings of this pulse, the spectra that we retrieve are really quite similar to one another, and the phases that we retrieve are more or less identical to one another. We then can also characterize the carrier envelope phase, and so here I show two measurements for different. So we insert calcium fluoride wedge pair to change the carrier envelope phase. And so here I'm showing two different measurements with two different insertions of the calcium fluoride wedge pair, showing that we can retrieve the carrier envelope phase oscillations without seeing much change to the pulse envelope measurement. So this is showing that the pulse envelope measurement is really quite robust. Okay, we would like to extend this beyond the mid-infrared. And so we adapt the same technique, but go back to this band fluorescence measurement. So using a zinc oxide crystal, and now detecting the spatial variation of this band fluorescence signal. And so here we have a measurement of the fundamental only band fluorescence signal, and with the fundamental plus perturbation. And so this is the oscillation pattern that we get here is showing the electric field measurement that we do with this tiptoe based on the band fluorescence. And the blue curve is showing a measurement of the same pulse using frog technique. And here this is showing as under review, but this paper was recently published in APL Photonics. Okay, so what can we learn from field sampling measurements? So the first thing that we thought about was looking at optical nonlinearity in materials. And so we know, for example, that if we expand the polarization, the time-dependent polarization field of a material, then we have terms that correspond to the linear response, which is the dispersion, the second order response if we have a broken inversion symmetry material. So this would be things like second harmonic generation or difference frequency generation. And then a third order response, the Chi3 response, which includes things like third harmonic generation, four-wave mixing, and self-phase modulation. And so the first thing we wanted to do was just to see if we could actually extract these responses from a material. And we focused initially on our third order response, and particularly on the self-phase modulation, because this appears at the same frequency as the laser and manifests as a intensity-dependent phase shift. Okay, so our phase shift for SPM is proportional to the intensity. And so we would expect that if we have SPM, then what we will have is that if we measure after propagation through the material, so in this case, we did two measurements, one where the intensity on the film, this is a zinc oxide thin film, one where the intensity was low and one where the intensity was high. And so what we expected to see was that on the leading edge of the pulse, we would have no or very small phase shift because the intensity is small. As the intensity increased, we would expect an increasing phase shift, which we do see here. So you can see there's a phase shift between the black and the red curve. As the intensity increases, that phase shift gets bigger. And then we would expect that as the intensity goes back to zero, then we would expect the phase shift to go back to zero. Now, of course, this is not what we see in this curve. So you see that the phase shift that we measure actually persists for long times. And so one might ask why this phase shift persists. And so we can look at this in another way. So we can calculate now using this nonlinear polarization, calculate what is the energy that's transferred to the material. And we calculate that energy transfer as a function of time in this gray curve, and then the integrated energy transfer in the black curve. Okay, and essentially what you can see here is that we're getting energy transfer in each half cycle of the pulse, which is leading to like a stepwise excitation in the excited state population. And so this is happening. This is showing that we're getting excitation on subcycle timescales. That excitation is persisting. And so what we're measuring in that persistent phase shift is actually something akin to the plasma phase shift in nonlinear optics. We've also extended this technique recently to measure what's known as the vibrational nonlinearity in fused silica. This is actually a quite challenging problem to measure because in fused silica, it's an amorphous medium, and so the vibrational excitation dephases within roughly 10 femtoseconds or so. And so here, what we do is we measure two different waveforms, one after nonlinear propagation through our fused silica sample, one which is a reference, and then we take the difference between those two, and what we get is this blue curve. And if we look at the blue curve only on the red side of the spectrum, then we can see that there are some slow oscillations in this pattern, in this difference. We then take the Fourier transform of that to look at the frequency response, and we get this red curve that's shown here with the error bars from our measurement. Now, this is essentially giving us some information about the delayed nonlinearity. And so we can compare that to the Raman response, which can be measured spectroscopically. And so that Raman response is taken from a paper from 1982. And so here we can see that our spectral response is agreeing reasonably well with that measurement. But now we're actually able to measure this vibrational contribution to the nonlinearity and how it dephases on very short timescales. Okay, I don't have a lot of time remaining, so but I would like to talk a bit about our spectral measurements using high harmonic spectroscopy. And so perhaps I'll go a bit quickly through some of the introductory materials, since probably people are fairly familiar with the discovery of high harmonic generation in crystals by Jamir et al. In 2011, and the explanation of how this works using how this process works in the momentum space picture. Okay, the HHG spectrum from materials encodes a lot of different properties. So things like symmetry, electronic band structure, topological properties. But it's a question, there's an open question about how to extract all of this information from HHG measurements. We choose to work in zinc oxide because it has some interesting behavior associated with its symmetry properties. So zinc oxide has broken inversion symmetry along the C-axis. And so if you do a measurement of the high harmonic spectrum in zinc oxide as a function of the angle between the laser polarization and the crystal's optic axis, then you can see that along the optic axis, we get both even and odd harmonics, and perpendicular to the C-axis, we get only odd harmonics. And so this is just a characteristic feature associated with this broken inversion symmetry along the C-axis. We're interested in getting dynamics about this, so we take our few cycle CEP stable mid-IR pulses, and we also look at this carrier envelope phase dependence of the high harmonic spectrum along two different crystal directions. So one is along the gamma M direction, which is perpendicular to this symmetry breaking axis, and one which is along the gamma A direction, which is the same as the symmetry breaking axis. And so what we can see in these measurements is that we actually have a different periodicity in the carrier envelope phase dependence. So again, this is not unexpected because if we have broken inversion symmetry, then essentially what that does is it makes the electron trajectories let's say in the laser field pointing up direction different from the electron trajectories in the laser field pointing down direction. And so therefore, we don't have a half cycle periodicity in the high harmonic generation process, but rather a full cycle periodicity characterized by a 2π periodicity. This is not the only difference that we see in these measurements. So we also can see that along the gamma A direction, there are a couple of minima that appear in the spectral domain that do not appear in the gamma M direction. So here, looking at the spectrum, you can see that the CEP-dependent spectrum, you can see that there's a weak minimum that's appearing at certain photon energies. What we did was we integrated the spectra for all carrier envelope phases, and we plot now the ratio of the gamma A to gamma M intensity to look at those interference fringes. And we see that they actually have a well-spaced, they're roughly evenly spaced, and they have a spacing of about 0.9 eV, which interestingly is not twice or not equal to a multiple of the photon energy. So this is not something that's coming just due to temporal dynamics of the field itself, but rather looks like it's coming from temporal dynamics in the material. So in case of spectral minima and high harmonic generation, it's often the case that we then can look at the trajectories and look for interfering trajectories. And so in this case, I'm just highlighting an example. So here we can think about having trajectories that are launched near the gamma point, but go to two different conduction bands. Then we can have those trajectories that end up at the same final position in energy momentum space. Therefore, they'll give rise to the same photon energy in emission, but with a time delay between them. Okay, and so this is what we think is that this minima we think are a signature of trajectory interference, and so we're working with theoreticians to identify exactly what those interfering trajectories are. Okay, with that, I think I'm going to talk very quickly about switching valley polarization in 2D materials. So in 2D transition metal dichalcogenides, or TMDCs, it's well known that there is what's called the valley polarization selection rules. So in these materials, you have two energy degenerate valleys, what are called the K and the K prime point, which respond to either left-handed or right-handed circular polarization, respectively. So one can imagine a situation where you might be able to excite at one valley using one-handedness of polarization, then somehow drive population to the other valley, and then observe that this population has transitioned through emission of a circularly polarized photon of the other handedness. Now, this was high harmonic generation in two-dimensional molybdenum disulfide was looked at before by David Rees's group. And what they found was essentially an anomalous perpendicular polarization in the high harmonic spectrum. And so here they're showing even harmonics in these bottom plot, showing even harmonics that are generated with polarization that's perpendicular to the driving laser. They explain this through by invoking the Berry curvature, which drives an anomalous current in the orthogonal direction. Now, this can also be understood from the point of view of selection rules. And so I'm going to click through this, but essentially the main point is that if you think about the trajectories that are launched in subsequent half cycles of the field, trajectories that are launched, let's say, at the K point. So this is driven with linearly polarized light. So both the K and K prime points are populated equally, but they will drive trajectories in the conduction band and in the valence band that look quite different from one another. So you have trajectories from the K point that are not the same as the trajectories that are launched at the K prime point for a given half cycle. However, if you look at the subsequent half cycle, now the trajectories that were launched at the K prime point look like the trajectories that were launched at the K prime point in half cycle 1. Okay, so in the from half cycle 1 to half cycle 2, you have this kind of symmetry between the K point trajectories and the K prime point trajectories. And this was shown by a group in Japan to lead to selection rules for the odd and even harmonics that give rise to perpendicularly polarized even harmonics. We decided to look at this, and we started with simulations using the Salmon code. And just looking at, in this case now, this is the parallel polarized harmonics and the perpendicularly polarized harmonics. It's actually quite difficult to extract much information from this. So here we're using few cycle pulses and varying the carrier envelope phase. We can see that there are differences in the patterns, but it's not obvious exactly what's going on. However, if we replot this to look now at the polarization helicity, so plotting this on the basis of right and left-handed circular polarization, now we can see something much more clear appearing, where for CEP change of pi, we have a change in the polarization for a given harmonic frequency from right-handed circular to left-handed circular polarization. And so this is evidence that what's happening is that we're driving population from one valley to another. So we're getting predominantly recombinations that are occurring at the K point, and then a half cycle later, we're getting, or with a pi phase shift in the CEP, we then can drive recombinations that are predominantly at the K prime point. I would just like to conclude. I hope that I've convinced you that these new platforms for waveform synthesis and sampling allow us to probe and control electron dynamics in solids. And I would also like to thank the sponsors of this research, specifically Air Force Office of Scientific Research, National Science Foundation, the U.S. Department of Energy, and the Gordon and Betty Moore Foundation. With that, I'm happy to take questions.
So if there are no further questions, or if you would like to talk to our speaker in a more private setting because you don't want to be all over the internet, just hang in there because we are going to finish the streaming. We thank Professor Chini once more for this really interesting talk. I think we learned a lot today about quantum materials. Take care, everyone. And if you are on YouTube, see you in 2 weeks.